Thanks for coming, and let's get started. I was creating this presentation for this talk, and I thought I could reuse some stuff from last year's presentation, and I searched for that file, and I got this back. 6 slightly different copies of the same file, or 6 variants of the same presentation. And these files are all slightly different from each other, but they're also very, very similar. And the problem here is finding anything is hard because all this is similar and you have to discern what's different among all these similar variants. This also happens in programming, especially in exploratory programming, where programmers work in a trial and error fashion and try out a bunch of different things and end up creating a lot of similar variants. Here is an example of a programmer who created a bunch of different variants of a game when he was exploring how the game looked. And these variants actually matter because programmers go back to them to explore a different thing or to reuse code and stuff like that. We know that finding code is already a hard problem, and having such similar variants just makes it really hard. So what can we do about this? We think Information Foraging Theory, or IFT, can help. It's a theory of how people search for stuff, look for information, and has been proven to be useful in a lot of different domains, including programming. And here is what the theory says. People seek information the way animals find their prey in the wild. And the theory has a few constructs. There is a predator and a prey. Here, the predator is the programmer, and the prey is the stuff that he or she is trying to look for. The prey might be hiding in different locations called patches, such as methods. And a programmer could go from one patch to another using links, like clicking on a link from one method to another or scrolling above and below. And just like animals sniff at cues like hoof prints to go to their prey, human predators, in this case programmers, also use cues such as words in source code and use that scent to guide them to their prey. So traditionally, IFT has focused on foraging in a single variant of stuff, in this case, a single variant of a program. But when we applied IFT to foraging in variation situations, we'll call it variations foraging, we found that it was very different from traditional foraging. And so we wanted to understand this new variations foraging so that we can better support tools for variants and things like that. And today's talk is going to be about this variations foraging in depth. And like I said before, we'll talk about it in an exploratory programming domain because this problem is very important there. So how do we use IFT in this situation? One of the things that researchers have done before is to build IFT-based computational models to help understand how people forage in the presence of, how people forage in any situation. So in the programming domain, there is PFIS, which is a computational model, and it stands for Programmer Flow by Information Sent. And here is how this works. It looks at which patches a programmer has been to before. Remember, here patches are methods. It computes what scent the programmer would perceive and basically predicts where the programmer is going to go next. In this specific case, it outputs a ranked list of predictions for the next navigation. And then you could compare this against the actual navigation and see how accurate the model is. Okay, now that we know how PFIS works, let's diverge a bit and talk about why these models actually matter. The fact that we can use the theory's constructs and propositions to build such a model directly says that IFT is applicable to that domain. The second thing we can do with such a model is validate specific hypotheses, like do programmers navigate in one variant the way they navigate in the other variants? And the way we could validate such a hypothesis is we could stick that hypothesis somehow in the model and see how accurate that model behaves and use that as a way of validating this hypothesis. They provide insights for tool building, and finally, if the model does really, really bad, we know we have gaps in our understanding of foraging behavior. Now that we know models are useful tools for researchers, let's go back to PFIS. So PFIS can explain and predict how people navigate, how programmers navigate in a single variant of a program. But we want to understand how programmers forage in the presence of multiple variants. So PFIS is not enough. We extended PFIS to PFIS-V, which literally stands for PFIS for variants. And here are our research questions. The first one is, how can PFIS-V account for variants? This has kind of 2 parts to it. One is, how do we even represent these multiple different variants of a program. And this is important because we can view this as kind of how programmers think about variants in their heads, like their mental models of the variants. And the second is the predictive algorithm, and we can think about this as how programmers navigate based on the mental models of variants that they have in their head. And then the second one is how accurate is this new model. Let's look at the answers to these questions one by one. The first one is the data model. Before we talk about data models for multiple variants, let's first see what PFIS did for a single program variant. Let's say here is a programmer who wrote this little program. The two boxes are two files, and then they have some methods. Remember, methods are patches. And the way PFIS represents such a program is as a graph, where the patches, in this case the methods, become the nodes of the graph. And the links between these patches are represented as the edges. So here are some method calls, and they are represented as edges between these nodes. Like I said, adjacency is also a kind of link. So here, sum and average are adjacent to each other. So that's also represented in this graph. Remember, there were these things called queues that are stuff in the program that people use to navigate, such as words in the source code. They were also in the graph, but I'm not going to talk about that for this talk, but the details are there in the paper. All right, so that is a single variant of a program. But what happens when the programmer goes and creates a second variant? Let's say this program tries to modify this average method to check for division by 0. The simplest way we can represent these two variants of this program is by doing another very similar thing, just like PFIS did for this variant also. So that gives us models for two variants. And if a third variant comes where a programmer adds a new method, we get a third data model. So a really naive, very simple representation of multiple variants is to put all these disconnected subgraphs together and treat it as a variant space. And so we evaluated this really, really simple data model, which is PFIS. And to do this, we used data from a prior user study. And in this case, the participants were asked to reuse code from prior variants of a program. And we did this with 7 novice programmers because novices do exploratory programming all the time. And we got about 500 plus source code navigations. That's how many we predicted. And for accuracy, we used hit rate as a measure, which basically is the percentage of times the actual navigation was predicted by the model in its top 10 predictions. So we got an average accuracy of about 55%, which is actually good because we can explain over half of the navigations that programmers made. But the remaining 45%, what about them? They actually tell us that there are gaps in our understanding. And these gaps could come from two different places. One is, do our data models actually represent the mental models of programmers, the programmer's mental model of the variants? And the second gap, source of gap, is that the predictive model, does that actually represent or reflect how programmers navigate with these mental models in their head? Let us now explore each of these gaps, and we'll talk about the gap between the predictive algorithm and the programmer's navigation behavior first. So in the case of a single variant, a programmer knows about a patch only if he or she has seen it. And that is when they can actually make a deliberate navigation to such a place, right? And that is what PFIS models. And PFIS could only predict about 80% of navigations that all programmers made. But in the case of variants, a programmer can know about a patch or a method if he or she has seen a similar patch in some other variant, right? So if you see, here's an example of a participant. So she saw a method draw scoreboard in one variant, went to another variant and directly tried to look for draw scoreboard. But PFIS said, oh, you've not seen this variant before, so I cannot predict. But the programmer actually knew about what the content of that method and deliberately made that navigation. So PFIS-V accounts for this, and it predicted approximately 90% of all navigations, which is 10% more navigations. So the second source of the gap was to understand what mental models people had in their head and the gap between our data models and those mental models. Now, in order to better understand that, we tried to build 4 different data models. which made different assumptions about programmers' mental models. We came up with these based on our qualitative findings and prior work on programmer navigations. I'm not going to talk about them in detail, but all these 4 different data models yielded different accuracies, which means one of them is a much better representation of programmers' mental models than the other ones. So the best model was called this. We'll talk about it in just a moment, and it gave an average 65% accuracy with PFISV. But for individual participants, the accuracy was up to 75%. And here is what this name means. So this data model was aware of the fact that there could be similar patches in different variants. Remember this picture that we saw? There are 2 different averages. So we know that the black average and the red average are both averages, even though they've changed and are in different variants, right? So this model was aware of that. And then it knew that some of these patches could be exactly similar across different variants. For example, sum, it is not changed at all. So this is text-based equivalence. And then the model was also aware of what happened when patches moved around. So if you moved a method from a bottom of the file to the top of the file, then it treated them as different. This data model did. And because this was the best one, so here is an example. So average in the first one did not have anything below it, but then the second one had another adjacent method max to it. And it turns out this was closest to participants' mental models. So what this tells us is that we need to keep all these aspects in mind when we actually try and design for variants. But there is more to PFISV and data models than just this. And what we noticed was, in fact, there were fundamentally 2 different foraging behaviors that participants actually were involved in. So we categorized participants into 2 groups based on that. The first one had 2, and the second one had 5 participants. And what was different between them is that for the first group, the choice of the data model actually mattered, which means the 4 different data models yielded different accuracies. Whereas for the second group, the choice of the data model did not matter at all. Like, put in any data model and they yielded the same accuracies. And this was because the first group used only source code queues, which is modeled well by the PFIS family of models, or generally any IFT-based model, whereas the second group ended up using a lot of non-lexical cues, such as how the visual output of the game looked like, which is not modeled by the PFIS family or any other IFT-based model for that matter. And what this tells us is that there is a gap in the way we've been modeling stuff, and hence there is also a gap in our understanding of how programmers forage among variants. Therefore, we need to start thinking about non-lexical cues and IFT-based modeling if we really want to leverage IFT as a theory to build tools and stuff like that in the case of variants. In summary, we spoke about variations foraging and how it is a problem in exploratory programming. We spoke about how IFT could help and built a computational model to help us understand programmers' variations foraging. We spoke about the different data models and the best data model, and the algorithm and how the notion of known patches differs from the single variant situation to a multiple variant situation. And finally, the need for non-lexical cues in IFT-based modeling, or generally when we're talking about variations foraging. And I'm done.
Okay, I have a question. So it looks like you're doing with the non-lexical cues like a lot of different possible design options, and I was bringing developers in